Hey everyone, welcome back to the channel. Today we are diving into a super useful technique in deep learning, that is reusing pre-trained layers. So in this video, we'll cover what it means to reuse pre-trained layer in your models, why it is such a powerful technique, and finally we'll walk through an example in TensorFlow where we visualize the results and see what's going in under the hood. All right, let's get started in understanding the concept of pre-trained layers. So what exactly is the pre-trained layer? So pre-trained layers are the layers of a neural network models that we trained on a massive data set, often on tasks like image classification, object detection, or natural language processing. So these models are usually trained on a large data set like ImageNet, which has millions of labeled images, or text corpora of NLP. So why we use pre-trained layers? Well, training a neural networks from scratch require a lot of data, time, and computational resources. Instead, you can reuse pre-trained models and fine-tune it for your specific task. For example, let's consider a pre-trained convolutional neural network, CNN, like ResNet or VGG, which have learned to identify edges, texture, and the basic features from thousands or millions of images. Instead of training your model from scratch, you can reuse those learned features and fine-tune the later layers to specific what is required in your task. And let's break it down. The main reason why using pre-trained layer is beneficial. So some of the benefits: first, it saves time and computing resources. So pre-training models on large data set takes days, if not weeks. And by reusing the pre-trained layers, you save the time and avoid needing massive computational resources. Second is better generalization. So these models have already been exposed to a wide range of data. So they can generalize well to a new and unseen data. And fine-tuning the later layers for your specific task allow you to leverage that knowledge. Third, improved accuracy with limited data. So if you don't have a lot of labeled data for your specific task, pre-trained models are a game changers. The models has already learned from general features. So your fine-tuning task might only require a small amount of data to get a good result. All right, now let's understand why this is so powerful, and let's jump into actual coding example using TensorFlow. So for this, we'll using the ResNet 50 and as a pre-trained layer, and we'll generate some random data and train the model. All right, so let me run those libraries, load those libraries in. And yep, and let's also will generate some render data for our model. This will be images and labels, perfect for testing our workflow. So in the random data, I'm taking 100 samples, a small sample, and this will generate our label data. And I've also changed the Y to the categorical using the one hot utility, right? Two categorical Y, two num classes. So num classes are only two. So we are using two classes here. So after importing the necessary libraries, we have generated the random data. Now let's move to the next step of loading the pre-trained model. So I will run this cell. Also, we will remove the top classification layer since we'll add our own custom classification, right? So freeze the pre-trained layer. And this is the custom layer which we will add in our on top of the pre-trained layer. And this is our model. And let me compile the model and show you the summary. So what we did just now, we loaded the ResNet 50 with argument including top equals to false. To exclude its final layer, we freeze the base layer so they don't get updated during training, which preserve the features that have already learned. Next, we added the custom layer, a global average pooling 2D layer to reduce the spatial dimension, a dense layer with 1024 neurons. And finally, the dense layer for classification. So which uses the softmax activation to handle multiple classes. So this is the part we have done. And right now we are just working with the binary labels because our classes is only two, but it's fine if you are using the softmax max activation here. And to make the training more robust, we'll use the image data generator to apply random augmentation like rotation and flip during training. So for that, let's go to our cell. So we scale the image to 0, 1 range, then apply the augmentation like random rotation and flipping to make our model more robust and help it generalize better. Now it's time to train the model. So let me run this cell. So we'll use the fit method to tell the TensorFlow to run 10 epochs with the base size of 32. And so our model is getting trained right now. So we train the model, but remember, since we are using the random data, we are not expecting any meaningful results. The purpose here is to understand how the training process works, not to actually perform the image classification. In the next two cells, I will be visualizing the accuracy and the loss over the epochs. And let's see how that looks in the graph. All right, it's almost done. Last iteration is left. Yeah, all right. So let's visualize the training process. We'll plot the accuracy and loss over the epoch to see how well the model is learning the random data. So if I run this, right, these are the two graphs. So here you can see the training accuracy and loss plotted over 10 epochs. Since we are using the random data, these curves won't show any meaningful trend, but I can see the loss getting in downward trend, which is good. But they will just so this actually shows how to monitor training process in the real world projects, right? So accuracy, I see it is with almost like 7 epochs, the accuracy is almost 6.5, which is good considering this is random data. So, yep, this is the we have successfully trained the ResNet 50 models on random data, and we have covered everything from data generation, model setup, and training to visualize. Now you know how to reuse pre-trained model like ResNet 50, even if you don't have the data set ready. Thank you for watching. I will see you in the next video.